Hey everybody! So we are into a new chapter, the beginning of our test, I believe it's test 4 unit, is gases. Okay, so for our test 5 we'll talk about gases, liquids, and solids. We'll get into intermolecular forces, we'll get into covalent solids, things like glass, and we'll talk about gases, of course. So lots of conceptual and math stuff in this chapter. You're going to be able to identify which gases act more like real gases, which we talked about last year. You're going to be able to do some gas calculations using PV equals nRT, as well as those other combined gas laws. And then you're going to be able to also tell like how gases act at a molecular level, called kinetic molecular theory. So a little bit of math, a little bit of kind of conceptual stuff, but overall not too bad, and should be something that you're familiar with. But first things first, we got to talk about gases and write down some things about them that we know. Gases, what do we know about them? First thing we know about gases is that they expand to fill their container. Right. Gases are fast moving. They don't really attract to themselves too much, right? They're bouncing all around. They're not like liquids that are closer together, and they're definitely not like solids, which are really compacted together, right? Gases fill their container. So if I put gases in a container, they're going to move all around, bounce about, hit the edges, and fill it as much as possible. Gases, they flow just like liquids. Gases are going to go to the area of least resistance. They're going to go where there's less pressure, where there's more volume. Okay, they're going to flow to areas just like you would see with liquids. And another thing we know about gases is that they are compressible. They are compressible. They're the only state that really is compressible. Liquid is a tiny bit compressible, but not really at all, okay? That's why we have hydraulics, right? We have liquids in those pipes that help us lift things that maybe are heavier. But gases are compressible. We could bring them in closer together and eventually make them into liquids and gases by compressing them. So those are 3 things that are just good to know about gases. Next thing we need to talk about is ideal gases. Okay? Ideal gases was just something that scientists came up with in order to do kind of simple calculations in gases to kind of predict what they're going to do. Each gas is different. Each gas gives off a different pressure in a container. Each gas moves at a different speed. So there were just too many calculations going on from gas to gas. So what we did is we made an ideal gas. And what are ideal gases? They are imaginary gases that fit the KMT. What is the KMT? That is kinetic molecular theory. What is kinetic molecular theory? We'll talk about that in a little bit. But again, ideal gases, these are just a certain set of parameters that we gave them so that we could do some simple calculations and predict what gases do. Ideal gases are not real. Okay, again, it's just like this nice situation, so we can just have a rough estimate of what real gases are going to do. So, kinetic molecular theory. What is the kinetic molecular theory? Well, part 1 of it is that gases consist of tiny particles. Okay, gases don't always consist of tiny particles. Things like CO2 are pretty big gases. Things like sulfur hexafluoride are very big gases. But with ideal gases, we just assume they're a tiny particle. Every single gas is just a tiny particle that moves around really fast. The other thing about kinetic molecular theory is that gas collisions between themselves and the container are elastic. What does that mean? Gas collisions between themselves and the container are elastic. That means that they don't stick together, okay? They're not even attracted to each other a little bit. Real gases, they bump into each other. Sometimes they stick together and then move a different way. Sometimes they slow each other down because they are a little attracted to each other. Okay, but in kinetic molecular theory, they're just bouncing off of each other. They're not even sticking whatsoever. They bounce off of each other and move the same speed in another direction. Let's keep going. Alright, with kinetic molecular theory, no kinetic energy is lost. In collisions. Okay? Typically, real gases, when they collide, they lose a little bit of energy, right? From friction, they'll bump into each other and slow down, just like people would. But with kinetic molecular theory, they bounce off of each other and leave in the opposite direction without any slowness of energy, okay? So they're just moving all over the place at the same speed, not slowing down, moving without a loss of any energy. The next thing are in constant rapid motion. So gas molecules are always in constant rapid motion. They're not slowing down, they're not sticking to each other, not stopping, they're always moving. Real gases, they do stick together, they do slow down. Sometimes they condense in the water, okay? Or liquid, sorry. Next one. No forces of attraction between particles. I talked about this before. Okay, real gases are attracted to one another. They sometimes stick together, sometimes slow down and condense into liquid. Okay, with ideal gases, they don't do that. And the last thing about kinetic molecular theory is that the kinetic energy of the gas particles depends on pressure. Okay. Usually, the less pressure, the better, or the quicker, I should say. Less pressure on the gases, they're able to move around a lot quicker. When you start putting pressure on those gases, they'll bump into each other a little bit more at first, but if you keep compressing, sooner or later they're going to slow down, they're going to stop, they're going to turn to a liquid, and then it'll turn to a solid. Okay, so less pressure, quicker they are. More pressure, the slower they are, and they stick together more often, if they were real gases. Alright, so ideal gases, again, you're just thinking of them as little tiny particles that move around, don't attract to one another, are just hitting the edge of that container and creating pressure and probably some temperature and things like that. What we got to talk about now? So your calculations will involve ideal gases, but we got to talk about real gases. Real gases deviate from ideal behavior when they get heavier. That makes sense, right? Ideal gases are supposed to be small, quick moving, don't condense with one another. Well, the heavier we get, the less ideal we get. The more they're going to slow down, the more they're going to stick together, the more they're going to be attracted to one another. Okay, so the heavier we get, the most deviation from ideal we get. So if I have these gases here, okay, I would ask you which one deviates from ideal behavior the most. And I said it was the heaviest. Well, how do we figure out the weight or molar mass of these compounds? We use the molar mass. Okay, so I'm going to quickly write down the molar mass of all these guys. This is 16 grams per mole for methane, or CH4. Neon is 10 grams per mole. It's not diatomic, it's by itself. Oxygen, you should know, is 32 grams per mole. And CO2, you probably should know, is 44 grams per mole. So I might ask you, which one is the most real gas? Which one is the realest? It deviates from ideal behavior the most. That answer is going to be CO2. It's the heaviest. It's most likely going to slow down when it bumps into other molecules. It's most likely going to be attracted to one another most because it's so heavy. And then I might ask you which one acts the most ideal, and that's going to be neon. Neon is going to act the most ideal. Okay, it's the smallest, it moves really quickly, it bumps into things, and then bounces off real easily. Okay, so that is how we know how things deviate from ideal behavior. Okay. One thing to know about real gases, real quick. Real gases condense when pressure increases due to attractive forces. Okay? Real gases condense. Okay? CO2 condenses when you increase the pressure, right? That is because you're bringing them closer together, they're colliding more, they're going to stick together and become more of like a liquid if we increase that pressure. Alright? It's also good to remember that when things condense, what's going to happen to the pressure inside of the container? Okay? If things are moving quickly and hitting those outer edges of the container, the pressure is going to increase, right? Because you're hitting the container, you're increasing the pressure on that container because things are bumping into it, little tiny particles. But if we have real gases in there, okay, they're not going to be bumping on those walls as much because in real life, they actually condense. They're going to hit one another and they're going to stick together and they're going to slow down. They're not going to hit that container as much. So the pressure is going to decrease. So I want you to be thinking about that conceptually, how real gases can kind of, what they will do and how that will affect things like our pressure, how that will affect things like our volume, and how that will affect things like our temperature, right? Temperature increases when particles collide more, pressure increases when particles hit the container more, volume increases when the particles hit the container more because they kind of expand those outer walls of our container. So be thinking about that when we're talking about ideal gases versus real gases and when I'm asking you conceptual questions of that nature. Everybody, the next thing we are talking about are our gas laws. So these are calculations that help us figure out certain things in ideal situations. So with all these gas laws, we're dealing with ideal gases. So what we have to know about gas laws is what we measure things in. Okay, pressure. Pressure, when we plug pressure into our equations, we got to make sure pressure is in ATM, okay? Atmospheres, right? So atmospheres is just the pressure of the atmosphere. At sea level, you are experiencing a pressure of 1 ATM. That's the pressure one atmosphere has on you. As you get higher up into the mountains, there's less atmosphere pushing down on you. You might get into the 0.96 ATM range. If you got below sea level, you're getting more pressure on you. You might be feeling like 1.02 ATM. Some conversions you might need to be able to make, which we dealt with last year, is 1 ATM equals 760 torr. Right, Torricelli was the guy who dealt with pressure. He got that unit named after him. 1 ATM also equals 760 mmHg. They like to throw that at you from time to time. And another one I'll just throw in there is 1 ATM equals 101.3 kilopascals. Okay, Pascal was another guy who dealt with pressures and gases, so he got a unit named after him as well. So pressure, make sure it's always in ATM. If I have 720 torr, just divide by 760 torr, and that'll give you how many ATMs there are. If I have 100 kilopascals, just divide by 101.3 kilopascals to get ATM. Next thing you need to know is that temperature going to be in Kelvin. Okay, it's always going to be in Kelvin. Make sure that if they give you Celsius, you're adding 273 to it. So Kelvin, right, it's just Celsius plus 273. One they love to give you is 25 degrees Celsius. Okay, that's 298 degrees Kelvin. They love to give you 30 degrees Celsius. That's 303 degrees Kelvin. Make sure that your temperature is in the correct units. And then volume. Has to be in liters. Since gases like to move around and fill the container, they usually take up more space. So we deal with liters instead of milliliters. And just make sure you know how to do the conversion from milliliters to liters. You should know that if there's 1,000 milliliters, that equals 1 liter. If I have 300 milliliters, that's 0.3 liters. If I have 5,000 milliliters, that's 5 liters. Okay? So know how to do that. Make sure that your pressure, temperature, and volume are all in the same units. One other thing that you need to know is STP, which we have dealt with before. STP stands for standard temperature and pressure. Standard temperature and pressure. And it's just basic situations that we put gases under. That's pretty much like the standard that we do some of our calculations at. At STP, when you have 1 mole of gas, so 6.022 times 10 to the 23rd molecules of a certain gas, okay, the pressure will be 1 atm. The temperature will be 273 degrees Kelvin, and the volume will be at 22.4 liters. So if you see STP, you can think 1 atm, 273 degrees Kelvin, 22.4 liters. Sometimes the volume will change, okay, but STP is usually always 1 atm, 273 degrees Kelvin. So let's go ahead and let's get into our actual gas laws and our gas law formulas. The main guy that we care about is the ideal gas law. The ideal gas law will actually give us all our other gas laws. So we have ideal gas law, which is the Mac Daddy of them all, which is PV equals nRT. We can derive any of our other gas law equations from PV equals nRT. Let me explain this. You probably remember it from last year, but P equals pressure, which I said before is in ATM. V is in volume, which is in liters. N is in moles. Okay, that's how many moles of the gas that we're going to have. R is a constant. It's the same thing every time. It's 0.08206 liter atmospheres per mole Kelvin. It's just our constant. And then T, of course, is temperature. Which is also in Kelvin. Okay? This is the only gas law they will give you on the AP exam. Okay? But you should be able to deviate the rest of the gas laws. And I'll explain here in just a second. One of our gas laws is the combined gas law, which is P1V1 over T1 equals P2V2 over T2. Okay? And you might be saying, I really don't want to remember that. That's a lot of work. I don't want to remember that whatsoever. You don't have to. You could use the ideal gas law to help you figure it out, okay? If you want to go ahead and figure out the combined gas law, say you get a question that wants you to compare initial pressure, initial volume, initial temperature to the final pressure, the final volume, and the final temperature, we just use the ideal gas law to help us figure out that equation, right? If I want to get pressure, volume, and temperature together on one side, for the ideal gas law, I would just have to divide by T, right? If I divided by T, that would put pressure, volume, and temperature on the same side, hey, that looks a lot like my combined gas law. Okay? Say I wanted to have an equation where I just compared pressure and volume. Okay? I just want an equation where I compare initial pressure and volume to final pressure and volume. Well, let's look at our ideal gas law. How would I get pressure and volume by itself? Well, look, we're lucky here because pressure and volume are already together. So an equation where we can compare initial pressure and volume to final pressure and volume would just be P1 V1 equals P2 V2. Okay, this is known as Boyle's law. Say we wanted to do a equation where we're just relating, let's go with volume and temperature. Okay, how would we get volume and temperature by itself? Well, to get volume and temperature together, I'd have to divide by T. To get rid of pressure, I just divide by P as well. Okay, now that I have volume and temperature together, V over T, okay, that's my equation. If I'm just talking about volume and temperature, I could say V1 over T1 equals V2 over T2. And that is Charles' law, right? So again, we're just deriving that from our ideal gas law. Now say our last one, which is comparing pressure and temperature, right? Well, again, I want an equation where I could compare initial pressure and temperature to final pressure and temperature. All I got to do, right, is get pressure and temperature together on my ideal gas law equation. Divide by V, divide by V. P and T are now together. So my equation that compares pressure and temperature is P1 over T1 equals P2 over T2. And that is Gay-Lussac's law. So, you do not have to memorize every single gas law equation. All you need to memorize is Pivnert. PV equals nRT. So let's go ahead and do some examples with PV equals nRT. Alright everyone, so our first example is a balloon of volume 253.2 milliliters at 356 degrees Kelvin has its volume decreased to 165.4 milliliters. What is the new temperature? Okay, so we're thinking ideal gas law, or it could be any other of our gas laws that we talked about. Well, let's figure out what we got to use. So here I'm dealing with milliliters, that's a volume, right? So I got a volume and I got a temperature. And then I get another volume, so I'm getting a second volume for some reason. So I got a V1 and a V2, and then it's asking me for a new temperature. So I also got a T1 and a T2. This isn't going to be an ideal gas law problem. It doesn't have moles in it. It doesn't have pressure. Okay, I'm just dealing with volume and temperature here. So let's go ahead and derive an equation that just deals with volume and temperature. And we could do that by using our ideal gas law. We're actually not plugging things into our ideal gas law, but we're going to use it to help us derive an equation between volume and temperature. Again, how am I going to get volume and temperature by itself? Let's get T over here, right? And then we got to get pressure out of there, right? So let's divide by pressure. Okay, so now it's going to be volume over T. Okay, so we could go ahead and derive an equation that V1 over T1 is going to equal V2 over T2. Okay, so now we've derived an equation to help us solve this problem. First of all, let's think conceptually what's going to happen here. We have a balloon, right? It's at a certain temperature and it's got a certain volume. If we decrease that volume, okay, if we decrease that volume, those molecules aren't going to be moving quite as fast. There's going to be less space for them. What's going to happen to that temperature? Well, if we decrease the volume, giving them less space to move around, okay, slowing them down a little bit, that temperature is going to decrease as well. So we should be looking for, we're looking for an answer that should be lower than 356 degrees Kelvin. Okay, think about that. Again, this is ideal gases, so they're always going to be moving. They're not going to be bumping into each other or sticking to one another, as much as real gases. So if I decrease that pressure, they're going to slow down, and that temperature is going to slow down as well. So let's go ahead and let's start plugging and chugging into our V1 over T1 equals V2 over T2 problem. Our V1, initially, our initial volume is 253.2 milliliters. We got to change that to liters, so that's going to be 0.2532 liters, right? You just move that decimal over 3 or divide by 1,000. Our initial temperature is going to be 356 degrees Kelvin. That's okay, because it's in Kelvin. Our second volume, it's 165.4, so it'll be 0.1654 liters. And our T2, we gotta have something to solve for, right? So our T2 is gonna be our question mark. Let me go ahead and erase this, and we'll start plugging and chugging. V1 is going to be, like I said, 0.2532. T1 is going to be 356 degrees Kelvin. V2 is going to be 0.1654 liters. And T2 is what we are looking for, which we can put as X. And now it just becomes a nice little multiplication problem. Let's go ahead and cross multiply in order to get things all on the same page. So cross multiply, I got 0.2532x, okay, 356 times 0.1654 is 58.88, and I want to keep the units here because I want to see what's happening, right? If I took Kelvin times liter, that would give me Kelvin liters, and X times liters is just, again, liters. Again, I want to use my units to help me figure out I'm on the right path. And then I got to get X by itself, so I'll go ahead and I'll divide by 0.2532 liters, divide by 0.2532 liters. X is now by itself, and look at that. Liters cancel out and leave me with Kelvin. I know I'm on the right track. So I'm going to take 58.88 divided by 0.2532, and I should get a new temperature of 232.6 degrees Kelvin. And that makes sense with my answer, right? We decrease that volume, those molecules are going to slow down, the temperature is going to slow down, right? So it makes sense, my units matched up, I used the ideal gas law to deviate that problem. Make sure that you're able to do that with all types of gas law problems. Alright, let's do another equation here. We have, what is the mass of oxygen gas at 20 degrees Celsius, 0.95 atm, and 3.2 liters? Okay, let's figure out what we have. We want mass, right? So let's just put mass as mass, because we don't know that. We do know that mass is measured in grams, okay? We have a temperature, which is at 20 degrees Celsius. Let's just go ahead and change that to what we need to change it to, which is Kelvin. So let's add 273 to that guy, which would make it 293 degrees Kelvin. Cool. Pressure they gave us, which is 0.95 atm. And they gave us volume, which is in the right units, which is 3.2 liters. Okay? So, again, we'll start out with our ideal gas law, and we'll go from there. They gave us temperature, they gave us pressure, they gave us volume. They didn't give us any other pressures or volume, but they want is mass. Okay? How can I use ideal gas law to get mass? Well, I know the identity of the gas is oxygen, and I know that I could figure out moles. Well, if I figure out moles, I could change moles to grams by multiplying by molar mass. So we are using the ideal gas law here. So let's go ahead and plug things in over on our right side. So pressure is 0.95. volume is 3.2. Moles is what I'm going to be looking for. And I'm going to run out of room. R is that constant, 0.08206, right? Sorry I ran out of space there. And our temperature is, see if I can squeeze it in, 293. I think I did it. All right, good deal. So let's go ahead and get moles by itself, right? So we're going to divide by 0.08206 and 293 on both sides. Okay, that gets moles by itself. Let's go ahead and plug this into our calculator. And if you want to do a units check to make sure everything's aligning up A-OK, feel free. 0.08206, oops. Let's go ahead and put that in parentheses. Times 293. So on the left side, we should end up with 0.126 moles of oxygen gas. Okay, so, but we don't want moles, we want mass, which is in grams, right? So to go from moles to grams or to mass, we gotta multiply by the molar mass. Well, oxygen gas, right? What is oxygen gas? Is it O? No, it is not O, it is O2. It's one of our diatomic molecules, okay? So it is O2, it can never be by itself. The molar mass of oxygen is 32 grams per mole. So we'll take 0.126 moles times our molar mass of 32 grams per mole. And where's my calculator? And we should get 4.0, let's go with 5 grams. 4.05 grams of O2. All right. That is it for our intro to gases, okay? Make sure you're using the ideal gas law to figure out all types of problems involving gases. Remember, you can manipulate that problem to get the rest of your gas equations, so you don't need to memorize all those gas equations. You could always use the ideal gas law to help you out. Have a great day.